Hey there, welcome back. This is the lecture that goes with week 10, chapter 5, part 2. And this week we'll be going over gas stoichiometry, and then we'll go over Dalton's law, and we'll go over root mean square velocity. And I also have kinetic molecular theory in here. We're not going to talk about it in this lecture, but I want you to read it. Okay. I want you to read over kinetic molecular theory in the slides. I want you to look over in the annotations and watch the videos linked to it in the annotations. Okay. There will be questions on it on the test and things like that, but we're not going to talk about it now in lecture. Okay, so let's begin with gas stoichiometry. Now, gas stoichiometry is always going to have two different parts. Okay, so let's go ahead and take a look at one type. And in one type, we're going to call this mass to volume gas stoichiometry, okay? And an example that we have for mass to volume is what volume of oxygen gas, that's O2, is needed to react with 5.47 grams of aluminum at 1.16 atmospheres and 21.1 degrees Celsius. And that's according to the reaction for aluminums plus 3 moles of oxygen gas, yielding 2 moles of aluminum oxide, Al2O3, and that'll be a solid as well. Okay, now the only gas that we have in here is this one, 3 moles of O2 gas, and we want to know what the volume is going to be. However, we do know these two pieces of information. Oh, hang on. This shouldn't be an A. This should be an and. There we go. Okay. So that means that this 1.16 atmospheres, this is our pressure. Okay. And this is our temperature. But we're not going to be able to use that temperature, remember, because we have to convert our temperature to kelvins. So I'll go ahead and put this down here. Pressure is equal to 1.16 atmospheres. And our temperature is now equal to 21.1 plus 273.15, or 294.25 kelvins. Okay. Now, remember that in the ideal gas law, PV equals nRT. And we know that this is going to be gas stoichiometry because we have this and we have this. We have our pressure, we have our temperature. We're looking for our volume, but notice that we don't have N. So at this point, we actually have two different variables. We have N, number of moles, and we have V, volume. Now we're looking for volume. That means that we need to figure out what N is first. Okay, so what we'll do is we'll come over here and say, okay, I see this 5.47 grams of aluminum. So we'll put that here to keep everything straight. Now, when we're going from mass to volume stoichiometry, what we're going to do is the first thing that we're going to do is we're going to do a stoichiometry of sorts, okay? And the second thing that we're going to do is we're going to use the ideal gas law. and that's PV equals nRT. Okay, so step one here is going to do stoichiometry. So we're going to start with that given, 5.47 grams of aluminum. Okay, and the next step in our stoichiometry is a molar mass. And the molar mass of aluminum, we would get that from the periodic table, and it's 26.982 grams of aluminum per mole. And this is just that standard stoichiometry format that we have seen before. Now, the next piece is that mole ratio, okay? And it's going to be from aluminum to oxygen. And that is that we have 4 moles of aluminum going to 3 moles of oxygen. But you see, remember, we need N. We're looking for N. And N is going to be moles of O2. And what that means is that this is where we're going to stop our stoichiometry, okay? And we can have 3 significant figures. So we say 5.47 divided by 26.982 equals, and then we multiply that by 3 and divide it by 4. And if I can have 3 significant figures, my answer for this first part is 0.152 moles of O2. And that is going to equal N. And now that I have that, I can go on to my next step, which is using the ideal gas law. And we're solving for volume. So we can set up volume is equal to nRT over P, and that's 0.152 times R, which is our ideal gas constant, 0.08206 times our temperature in kelvins, which we found was 294.25, all over our pressure of 1.16. Okay. So 1.152 times 0.08206 times 294.25 divided by 1.16. I can have 3 significant figures, and so this becomes 3.17 liters. Okay, and that's my final answer. So this was how we do a mass to volume stoichiometry, and that means that our given is a mass, and we're looking for a volume. All right, so now let's take a look at another case. In our second case of gas stoichiometry, we're going to have volume to mass. Okay. So let's go ahead and take a look at an equation that goes with volume to mass. Okay, and here I have the Haber process, which is N2 plus 3H2, also a gas, yields 2 moles of ammonia, NH3, and again, a gas. Okay? All right, so now in this one, the problem that we're going to say is how many grams of ammonia will you make with 20 liters of hydrogen gas at 5.42 degrees Celsius. Okay, so let's take a look at what we have here. So First of all, we're going from volume to mass. So here I can see that I have 20 liters of my hydrogen gas. And I'm at 5.42 degrees Celsius. So I'll say 5.42 plus 273.15, and that will give me 278.57 kelvins. Oh, and I just realized that I did not put a pressure in here. Okay, at 5.42 degrees Celsius, and we'll say 0.96 atmospheres. Okay, so our pressure is a little low. Not really low, but a little low. Okay, now we can come back here and say, now we also have 0.96 atmospheres. Okay, so we have pressure, volume, and temperature. And what we want to know is our mass, how many grams of ammonia we're going to make. So in this kind of a problem, volume to mass, our first step is going to be to use the ideal gas law, PV equals nRT. And our second step is going to be stoichiometry. So let's go ahead and start with that. So first of all, in this case, we won't be solving for volume, we'll be solving for N, number of moles. That's gonna always be our middle point. We're either using the ideal gas law to solve for N, or we're using stoichiometry to solve for N. But either way, we're looking for moles. Okay, so in this case, we'll have N equal to PV over RT, and our pressure is 0.96 atmospheres, and our volume is 20 liters. And R is our ideal gas constant, 0.08206, and our temperature is 278.57. And if you've already looked at the slides, you'll know that this one's a little bit different. Okay, so we have 0.96 times 20 divided by 0.08206 divided by 278.57. And what I get is I can have two significant figures now, so this becomes 0.84 moles. Now, it's really important to know exactly which moles we're talking about here. We're not talking about our moles of ammonia yet. We're just looking at hydrogen. We're just looking at what we have here for hydrogen, which means this is going to be 0.84 moles of our hydrogen gas. Okay, now for our second step, we're going to do stoichiometry, but we're going to start with this moles of H2. So we say, all right, well, we have 0.84 moles of H2 times, and now the next piece that we're going to put here is a mole ratio. Okay, so that's 3 moles of hydrogen and 2 moles of ammonia. And then the last piece is going to be the molar mass of ammonia. So we'll have 1 mole of NH3 on the bottom, and then 3 times 1.008 plus 14.007, and that will give me 17.031 grams of ammonia. Okay, now I do my stoichiometry, 0.84 times 2 times 17.031 divided by 3. And I can only have two significant figures because of the 0.84 moles here. And so this becomes 9.5 grams of ammonia. And that is how we would do gas stoichiometry, where we start with a volume and look for a mass. Okay, now let's take a look at a special case. And that is when we are at standard temperature and pressure. This is also known as STP. Okay, all right, so this is also known as STP, and it means a couple of very important things. First of all, it means that we are at 0 degrees Celsius exactly, or 273.15 kelvins. It also means that we are exactly 1 atmosphere in pressure. Okay, so based on that, there's something very important that happens here. This means that for 1 mole of any gas, volume equals 22.42 liters. And you can use this in your work, all right? And so, well, what do I mean by that? Well, what I mean is that if you are at STP, so let's say that we have a sample of 6.82 liters of carbon dioxide at STP, okay? And we want to know how many grams of CO2 do we have, all right? Well, what you can do then is you can say, okay, well, if I have 6.82 liters of CO2, and this would work for any gas, and we know that we're at STP, then we can say 22.42 liters of CO2 is equal to 1 mole of CO2. See, in a normal problem, you would have to do this whole problem for gas stoichiometry. Normally, what you would see, this is volume to mass, okay? And so you would need to do your PV equals nRT, and then you would have to find moles and grams, okay? But we don't have to do that because we're at STP. So we can just cancel out our liters with liters on the bottom, liters per mole. And then a molar mass, 1 mole of CO2, okay, and that's 15.999 times 2 plus 12.011, so 44.009, okay? So then we can say 6.82 times 44.009 divided by 22.42. And so this was grams CO2 here. And our final answer, we can only have 3 significant figures, would be 13.4 grams of carbon dioxide. So if you're at STP, you don't have to do the whole setup if you don't want to. You could easily do the ideal gas law and then a stoichiometry for this problem. But you just need to remember, if you're going to do this one, that STP means a temperature of exactly 273.15 kelvins and a pressure of exactly 1.00 atmospheres. Okay. All right, now let's take a look at another interesting thing, and that's dealing with molar mass and density. And this is the last part that we have in gas stoichiometry, and that is that you can link the molar mass of a gas to its density. And the way that you would do that is if molar mass is mm, we'll just say mm for molar mass, that's going to be equal to the density of the gas times R times T all over the pressure. Okay, so this mm is molar mass, and it's going to be in grams per mole. Okay, and our T is, of course, temperature in Kelvin. And our R, we know, is always at this point 0.08206. Okay. And D is our density in grams per liter. And last but not least, P is our pressure in atmospheres, like usual. Okay. So now we can ask any question for any molar mass. For example, let's say, what is the density of carbon dioxide at 15 degrees Celsius and 1.07 atmospheres? Okay, so in this case, our again, the first thing that we always do in this case is to change our temperature from Celsius to Kelvin. So 15 plus 273.15, and that gives us 288.15 kelvins. And I just found the molar mass of my carbon dioxide, but I didn't write it down. So 15.999 times 2 plus 12.011, okay, is 44.009 grams per mole. And now I'm going to be solving for density. Okay, so how do we solve for density? Well, what I'm going to do is we're going to have to move everything away from the density. So what that means is that density is equal to molar mass times pressure divided by RT. Okay, so that's 44.009 times our pressure of 1.07 all over R, 0.08206, times temperature, 288.15 kelvins. Okay, so now I type that into my calculator, 44.009 times 1.07 divided by 0.08206, and then it divided by 288.15. And I get a density of 1.99 grams per liter. Okay. You could work through something like that as well. So that wraps up gas stoichiometry. The next thing that we're going to look at is Dalton's law of partial pressure. And what Dalton's law of partial pressure says that the total pressure in any chamber is equal to each pressure added up. So you could say the pressure of gas number 1 plus the pressure of gas number 2 plus the pressure of gas number 3, and so on and so forth, all the way however many gases you have. Okay. Now, in order to be looking at this, one of the things that we're going to need here is another way to define concentration. So we've learned about mass percent, we've learned about molarity, and now we're going to learn about something called mole fraction. And mole fraction is a capital X, and you could say the mole fraction of gas number 1 is equal to the number of moles of gas number 1 divided by the total moles of all the gases. So let's take a look at what a problem for this might look like. Okay, I'm going to adjust one that we have in the slides just so that it's a little bit different. Okay, let's say that we have 4.07 moles of hydrogen gas and 7.82, that's supposed to be a 2, but it's a very messy 2, 7.82 moles of helium gas in a container at 2.78 atmospheres. And we could say, okay, well, I want to know two different things. We want to know what are the partial pressures of hydrogen and helium. But let's take this a step farther, and let's also say, what is the volume of our container? Okay, so let's take this in pieces. First of all, let's look at the first part of this problem. We'll call this number 1. What are the partial pressures of hydrogen and helium? Okay, so what we'll do there is we're going to need to work with another equation, and that is that the pressure of gas number 1 would be equal to the mole fraction of that gas times the total pressure. Okay, so actually I'll stay with pink so that I can sort of identify this as the first one. So that means that the pressure of hydrogen is equal to the moles of hydrogen, 4.07, divided by our total. And our total moles are 4.07 plus 7.82. 11.89 total moles of gas. And now we're going to multiply that by the total pressure of the chamber, 2.78. So we say, okay, 4.07 divided by 11.89 times 2.78. And what we get here is that the pressure of hydrogen is going to be equal to, I can see that I have 3 significant figures here, is going to be equal to 0.952 atmospheres. And then I can look at the pressure of helium. And that's based on our moles helium, 7.82, divided by our total moles, 11.89, times the total pressure in our chamber, 2.78. And I can have 3 significant figures, but I'm going to break the rules a little bit, and I'm going to go with 4, and you'll see why in a minute. And that's 1.828 atmospheres. Now, this is a very important thing to note, and that's if I take these two and I add them, 1.828 plus 0.952, I get 2.78. Okay, now let's take a look at this. I sort of tossed another piece of a problem here, and I said, what is the volume of our container? And the reason that I tossed that in is so that you could recognize a couple of things. Well, from this, we would use, again, the ideal gas law. And if the ideal gas law is PV equals nRT, and we're looking for volume, then V is equal to nRT over P. Okay, now the number of moles that we're going to use is going to be the total number of moles of gas in the chamber. Because remember, volume does not depend on the size of the particles. It depends only on the number that you have. So we're going to use our total number of moles, 11.89. And then we have our R value, 0.08206. And our temperature, which I didn't give us here. I would have need to give you that. So we'll say that we're at 25 degrees. So we'll say we're at 0 degrees Celsius because that makes life easier. Okay, you would have to be given that. Okay, so 0 degrees Celsius is 273.15 kelvins. I am running out of room. All right, divided by our pressure in our chamber, which is 2.78 atmospheres. Okay, so the volume of this chamber would be 11.89 times 0.08206 times 273.15 divided by 2.78. And this many moles in this chamber at this temperature would actually end up being 95.9 liters. Okay. All right, now let's take a look at what another possibility that we can do with Dalton's law. And that is the idea that you have a couple of different chambers of gas. All right, so let's take a look at a problem, and let's say that, and I'm actually going to show one that's in the slide so that I can draw a picture of it. All right, so this says 27.4 liters of oxygen gas at 25 degrees Celsius and 1.30 atmospheres, and 8.5 liters of helium gas at 25 degrees Celsius and 2 atmospheres. Okay. They're pumped into a chamber with a volume of, you know what, I'm going to change this just a tiny bit from the slides here. I'm going to make this a volume of 10 liters at 25 degrees Celsius. Okay, and I want to know the partial pressure of oxygen and partial pressure of helium and the total pressure. So this is a lot like a problem in the slides, and I just changed it just for a little bit to work with here. Okay, now let's take a look at what we're going to need to solve this. Okay, so first of all, what we're going to need to solve this, see how we have a volume, this 25, 25, 25, we're going to ignore the temperature. We have a volume and a pressure, and we have a volume and a pressure. And we're looking for, check this out, a volume and a pressure. All right, so now you stop and think, okay, well, wait a minute, how could I figure this out? Well, we're gonna go all the way back to last week, and we're gonna say, which gas law dealt with pressure and volume? Volume and pressure, that means Boyle's law. Okay, and remember Boyle's law is P1 V1 equal to P2 V2. Oh, okay. So for oxygen here, this is V1 and this is P1. And down here, this 10 liters, this is V2. And we just have to solve for P2. Okay, that means that the pressure of our oxygen is equal to 27.4 liters times 1.3 atmospheres divided by our volume now of 10 liters. And now what I have here is I can have, it looks like 3 significant figures all the way through, and so I can have 3.56, 3.56 atmospheres, gotta make sure that we're remembering our units, of oxygen. And now we can do it again with our hydrogen, okay? Well, that's 8.5 liters, sorry, not hydrogen, helium. I just now caught that shouldn't have been H2. That should be He, helium. There we go. So we have 8.5 liters of helium and 2 atmospheres. And our final volume is again just this 10 because it's going into the steam chamber. So now I have 8.5 times 2 divided by 10, and that gives me 1.7 atmospheres of helium. Now remember the total pressure, Dalton's law says that P total is going to be equal to the pressure of oxygen plus the pressure of helium. Okay, so that means that we have 3.56 plus 1.70. And we get a total pressure of 5.26 atmospheres. So you can't forget the beginning of the chapter because it's going to come back. All right, so now the next section in the slides and the annotations is the kinetic molecular theory of gases. And I want you guys to read those and watch the video links that are in there. And it's a great concept that you guys can look over. The last thing that we want to talk about is root mean square velocity. Oops. Now, it's not exactly the same thing, but we can basically think of this as gas molecule speed. Now, I know that speed and velocity are not the same thing, and you probably know that too. But this is a good way of basically thinking how fast are the gas molecules moving. Okay, and so this is where everything sort of gets turned on its head. Okay, root mean square velocity, RMSV, is equal to the square root, in parentheses, of 3 RT over M. Okay, but this is where things get a little bit tricky. First of all, T, well, you know, this has to be temperature in kelvins. We said that that wouldn't change. But now for this problem and for next chapter, we're going to learn a new R value. And it's different because because it's not liter atmosphere per mole Kelvin, it's joules per mole Kelvin. And so the R value that we're going to use here is 8.3145. That is a very messy 5. 8.3145 joules per mole Kelvin. And this capital M here is the molar mass of our gas in kilograms. Can't forget that because that's going to be different. Okay, so we could do any gas that we wanted. Let's say that we want to know what is the root mean square velocity of, let me look at my periodic table here and come up with something crazy, let's say, xenon at 100 degrees Celsius. All right, so how fast would xenon be traveling at 100 degrees C? Okay, well, first of all, let's think about what we need here. This 100 degrees C, 100 plus 273.15 becomes 373.15 kelvins. Okay, and the next thing that I'm going to need here is the molar mass of my xenon. Okay, but that's actually going to be a little bit different. Okay, the molar mass of xenon, according to the periodic table, is 131.29. 131.29, but that's grams per mole, and we need kilograms per mole. Okay, so that means that what we need to do here, let me go ahead and write this in a slightly different way, grams per mole. Okay, and that means that we have 1,000 grams per 1 kilogram, which means that in this case we have 0.13129 kilograms per mole. And you're going to always have to do that in order to do this problem. Okay, now let's go ahead and we'll come back to our calculation. And our root mean square velocity is equal to the square root. Okay, make sure that you do everything in parentheses before you take that square root. So 3 times 8.31, I keep saying the wrong thing. 45, all right, I bet this is confusing. Let me go ahead and make that a times, there we go. Times, in this case, we have 373.15 kelvins divided by our molar mass in kilograms, 0.13129. Okay, now, again, you haven't done this yet, so I want you to pull out your calculator. I want you to do it with me. Go ahead and pause the video while you're calculating. So I have 3 times 8.3145 times 300, try that again. 3 times 8.3145 times 373.15 divided by 0.13129. And then after all that is done, then I can take my square root. And what I get here is 266 meters per second. And that is the end of chapter 5. I'll see you in recitation.